All right, here we're gonna finish up chapter 3 by looking at inverse of trig functions. Let's first look at what the graphs of the traditional trig functions are. First, let's look at the cosine function. Then the sine function. Tangent function. Okay, we know that the sine and cosine function are bounded on the y-axis by 1 and -1. And they go on infinitely from negative infinity to positive infinity on the x-axis. At 0, cosine is 1. At pi over 2, cosine is 0. At pi, it's -1. At 3 pi over 2, it's 0. And at 2 pi, it's 1. And on the other side, just the opposite. So at negative pi over 2, at negative pi, -1, because it goes in the similar directions. This is why we say the period of cosine is 2 pi, because it repeats itself after 2 pi. The sine function is simply shifted pi over 2 units. So at 0, sine is 0. At pi over 2, it's 1. At pi, it's 0. At 3 pi over 2, it's -1. And at 2 pi, it's 0. At negative pi over 2, sine is -1 pi, and it repeats itself. Again, it's also bounded by 1 and -1. Since tangent is made up of sine over cosine, it is bounded by the cosine function on the x-axis. Anywhere the cosine function is 0, which is at negative pi over 2 and pi over 2, the function, it has a vertical asymptote. So at 0, sine is 0, cosine is 1, so it's 0, and it's an increasing function. So it looks like this. And there are asymptotes at every pi over 2 unit. And the graph repeats itself. So what we have to do now is we have to look at, well, we'll do the secant and cosecant and cotangent. But, well, let's do it. We'll look at those. We have the secant, we have the cosecant, and we have the cotangent. These bottom three are known as the reciprocal functions because secant is 1 over cosine, cosecant is 1 over sine, and cotangent is 1 over tangent, which means it's cosine over sine. So we see that the secant function has, again, it's anywhere the cosine is equal to 0, we have asymptotes. So at all the pi over 2 and pi over 2 intervals. Since it's the reciprocal function, what we do is reciprocate. We take the graph and just flip it over. So the secant function, it has a intercept at 0, it crosses at 1. And from where all the vertices are, the graph shifts. So instead of the cosine function looking like this, it reciprocates, it flips over. Likewise, the same thing with the cosecant function. So anywhere the sine is 0, it has a vertical asymptote, which is all at the n pi units. And since the sine function has a 1 there, it's reciprocated from that point. And from -1, it goes the other way. Again, you all should know these because you took trigonometry not too long ago. And the cotangent function. Anywhere the sine is equal to 0, that's where my asymptotes are. So it has asymptotes at the pi units and 0. Now this is the opposite because anywhere at negative pi over 2. Negative pi over 2, we have the sine is -1, cosine is 0. So these are my x-intercepts. We see that it's shifted over, but now is it an increasing or is it a decreasing function? So at pi over 4, it equals 1. Because pi over 4 sine and cosine are the same values. So we see that this function is this. So those are the trig functions. Because now we're going to look at the inverse of those functions. What are inverse trig functions? if y equals cosine x, the inverse, well, we would switch x and y. And if we solve for y, the y inverse would be the inverse of cosine. Now, for example, the graph of the inverse cosine function. Remember, in inverse functions, the domain of the original function is the range of the inverse, and the range of the original is the domain. So the domain of the original function of cosine is negative infinity, positive infinity. And the range is from -1 to 1. So it's all real numbers from -1 to 1. So what's the inverse cosine function going to look like? What's that? The graph, yeah. And what's that going to look like? So do I have a vertical or a horizontal asymptote? I have vertical asymptote because the domain of, the range of my first one was from -1 to 1. So my graphs have to stay within here. So what's the graph going to look like? There's the cosine function. Let's look at the first period. What happens here? No, look at first period for the cosine function. What's the inverse going to look like? In other words, let's look what's happening here for inverse functions. If originally we said, if I gave you the cosine of 45 degrees, what would that equal? Or I could cosine of pi over 4. Same thing. What would that equal? Remember, if you want to be engineers, you gotta know this stuff. Not wait to look it up somewhere, or this is basic trig. Square root of 2 over 2. That's what 45 degrees is, or pi over 4. That's the original. Now, when I give you the inverse function, I give you the solution, you have to give me the angle that gives me that solution. It's the inverse. It's the opposite. I give you the angle. I give you the angle, you give me the solution. The inverse is I give you the solution, you give me the angle. Isn't that what your trig teachers taught you? Okay, that'll be your homework for tomorrow, is to tell me the inverse graphs of each of those. And not only just draw it, you're just gonna cut and paste off the internet. You have people who explain to me why. I'm interested in the why something happens. I don't care what the picture, I know what the picture looks like. I gave you the pictures actually. I want to know why. So we will use, instead of angles, we use radian measures. So if given a degree, measure then you have to convert it to radian measure. By what formula? What about it? Just pi over 180? Yeah. Whatever angle you have in degrees, multiply it by pi over 180. The degrees will cancel, and then you'll have your radian measures. On your sheets I gave you last week, let's define these things. We're only going to look at the tangent, cotangent, secant, cosecant, because sine and cosine is pretty relatively Mickey Mouse. Not domain, definition. Y equals the inverse of tangent of x is the number in the open interval negative pi over 2, where tangent y equals x, where the tangent of the answer equals the angle, or the radian. Inverse cotangent is the number in the open interval, because we're always going to use either open interval or half open intervals with inverse functions. Where cotangent of y equals x. And remember, sine and cosine are simply pi over 2 units shifted. So therefore, so are the cotangent, tangent. So are the secant, cosecant from the sine and cosines. They're only pi over 2 shifts. The inverse of secant is the number in the half open interval 0, pi over 2, or pi over 2, comma, pi. Where the secant of y is equal to x. And lastly, the inverse of the cosecant is the number in the half open interval negative pi over 2, 0, union 0, pi over 2, close interval. Where the cosecant of y equals x. So what does all this stuff mean? The inverse of cosecant x is the number within that interval where cosecant y is equal to x. What does that mean? It's what we've been talking about. The inverse cosecant is I give you the angle, I give you the solution, you have to give me the angle which matches that. We're used to seeing this. That's what we're used to seeing. That's f of x. Once we do inverse functions, we are now doing x equals cosecant y. Now we're doing it backwards. So again, the faster you memorize the table, the unit circle of the table, life will be much easier for you. Especially if you want to get past calculus 3 and differential equations and complex analysis and do any of the stuff in engineering. Well, I'm not going to talk about because once you do your graphs, we can talk about them. Because also try to relate when you do your graphs of the inverse functions. Tell me if they're odd or even functions. Yes, you'll have to go back in algebra books and look up what odd and even functions mean. Hopefully you wouldn't because you're in calculus, but I know we're cramming a lot of stuff down your heads. We talked about it not too long ago in this class, actually. Example 1. Here are two values of the inverse tangent of x. One over radical 3 and negative radical 3. So what angle gives me this as a solution? You don't have to write that question down. I'm asking you in general. You have it right here. That's right here. What? Why pi over 6? How'd you get that? Again, I don't want you guys just to read the sheets I gave you. I must stop doing that. Because I can read it myself. I have it right there. If you give me an answer, you better tell me why. Why is it pi over 6? You're trying to see how it worked out and try to figure it out. You're not going to happen that way. It's either you know it or you don't. Because you won't see that anywhere, actually. On the unit circle, what will you see? What do you have to do? Algebra rules says do what whenever you have a radical on the bottom? Rationalize it. How do you rationalize 1 over radical 3? So it becomes radical 3 over 3. That is what you'll find in your charts. So the inverse tangent of radical 3 over 3 will give you pi over 6. What about this one? What's the difference between this one and this one? We see from the graph of tangent that the function is symmetric about the origin. What does that mean? What does symmetric about the origin mean? It tells us it's an odd function. If the angle's positive, then the answer is going to be positive. If the angle is negative, the answer is going to be negative. The answer is positive. The only way the answer can be positive is if the solution, if the radian is positive. The solution is negative. The only way that can happen is if we are in the fourth quadrant. And then therefore the answer of this one has to be negative as well. So what is the square root of 3 over 1? Angle of pi over 3. What is the degree in pi over 3? 60 degrees. Because 30 degrees would be square root of 3 over 3. Square root of 2 over 2, or square root of 3 over 2 would be pi over 4. Square root of 3 over 1 would be pi over 3. So again, if you look at this, the angles in which tangent moves, this is going to be the hardest part about inverse functions. You have to go backwards. Let's see if there's another example. Yes. Square root of 3 over 3? Yes, it is. It has to because it's pi over 6. Mm-hmm. You have to do some work because that's the reason we're doing now with the reciprocal functions, the rational functions. Again, sine and cosine is Mickey Mouse. We don't deal with those anymore. Not in this section. We're only going to look at the more difficult ones. You have to work it out yourself now. Instead of working out the proofs of the derivatives, on the back of your homework sheet I gave you, on the example sheet I gave you, oh, it didn't print out. That's the third sheet. Y'all don't have these? The derivatives of inverse functions. You know, not on that sheet. So that should have been the third sheet that didn't print out. That's I was having troubles with. All right, copy those down. Instead of going through the entire example and proof of and the examples of the exceptions to the proofs, go ahead and copy these down. Or take a picture of them. You should have them actually in those cheat sheets I gave you all. That was at the beginning of the semester. Has all the algebra formulas, the trig formulas, and the calculus formulas. Those are the cheat sheets. I don't. And the most important part of this sheet didn't come out. If you're just now starting to copy them, you won't have enough time. Okay. All right. Let's see how you use these now. Once you learn how to use these will save you so much time. Here's example 2. There it is. Oh, there it is. Example 2. Using the chain rule, calculate the derivative of the inverse sine of x squared. Find the derivative. So using our formula, I'll put the formula over here. where the absolute value of u is less than 1. So using substitution, what all do we have to find? Well, with the first using substitution, we have to first define what is this going to be called? That's going to be u. Then we have to find from there, we have to find the du dx. What's the derivative going to be? Now we can start plugging it in there. So the derivative of our function is going to be what? What is u? Yeah, u is x squared. So it's x squared squared times du dx, which is 2x. So our solution is 2x over 1 minus x to the what? To the fourth. Pretty straightforward and easy. What's example 3? Example 3. Y is equal to the inverse of the secant function of 5x to the fourth others. Where the absolute value of u is greater than 1. So to find our solution, again, we have to define u and we have to find du. U is whatever's inside the parentheses. And the derivative would be 20x cubed. Is it up or down? 5x to the fourth, yes. All right. So our solution will be, what goes in the absolute value symbol? 5x to the fourth. And again, it's the 5x to the fourth in parentheses squared minus 1 times du dx, which is the derivative of u with respect to x would be 20x to the third. Do we need the absolute values on this one? Yes or no? Can 5 ever become negative? No, it's constant. Can x to the fourth ever become negative? No, it's raised to the even power. It's always going to be even. So we don't need the absolute values. You only need it because, remember, the absolute values always have to be greater than 1. Since it's an even exponent, there's no way this inside here can ever be negative. So 5x to the fourth squared would be 25x to the eighth minus 1. So what's our next step? What can we do? Can anything cancel? $20 and the 5. So 5 goes into 24 times. Anything else? 3 x's are gone. So we subtract 3 from there, you're going to get 1. So it's just x. So it's 20 square root of 25 x to the eighth minus 1. And there is your derivative. You see how once you have these formulas, where are they? Once you have these formulas, the derivative of inverse functions, now it's just a matter of plug and play. Again, those are just numbers. These are just numbers. But what do they mean? It's the why do we do it? Can then what does it give us? What do these numbers mean? What does the derivative of an inverse function tell us? This is not a trick question. What does a derivative tell us? It tells us the rate of change. It's the rate of change of the inverse. Right. So again, you have to know these things. Because I know is if you're gonna go to Cal 2, you have to know these things because instead of looking back, everything okay? Okay, that's you don't have to say, you don't have to say.